Welcome to Algebra 2. This is section 1.1, getting started on the actual textbook material here in this class. So we spent a few days reviewing our Algebra 1 concepts. Now it's time to start looking at some bigger ideas. It's the title of our textbook. And also just kind of understanding math in a little bit more of a conceptual sense. Instead of memorizing formulas, this textbook really does a nice job of helping you understand and comprehend how mathematics ties together, which I think is a really crucial skill if we want to be good mathematicians, and kind of see how math connects, which is really a nice breakthrough moment for you. So today, to get this started, parent functions and transformations. We're going to learn at how in this chapter we're going to tend towards lines, but we're going to learn how changing values and functions, how that affects the graph of a function. And this is a really big skill for just understanding mathematics in general. So I hope you enjoy it. To start, we got, it says refresher from Algebra 1, but we've already done that. This is just an introduction into this lesson. We want to learn the names, kind of revisit some vocabulary, and just take a look at different graphs that can be produced. Now, we'll go through a lot of these in more detail as we move through the year, but we just want to familiarize ourselves with them now. So what I want you to do is take a second, and you can see I've got all the names and then the typical functions listed over here off to the left. I just want you to match them really quickly and see if you can't come up with why they make sense, or an argument about why they make sense. So if I were you, I'd pause the video, take a second and try and match these up, and then I'll get going here in a couple seconds. All right, so the first graph that we have here is a V-shaped graph, letter A. And it's important to realize that if we were to zoom out, this graph would continue to rise to the right and rise to the left. And what I notice is that the heights are along the y-axis, they're always positive in this case. So as we look off to the left, I would hope we would have chosen absolute value to be represented by graph A, because an absolute value outputs a positive result. Regardless of what is plugged in, it represents a distance, so it has to be positive. Letter B, here we've got an interesting function, and I notice that on the x-axis, what I could input into that function, there's nothing negative. So what over there on the left would not allow me to plug in any negative values? And hopefully it wouldn't take us long to find the square root function to be one that does not allow negative inputs. And again, this graph does continue off to the right, and it does continue to rise as we move on and on, but it will not allow negative inputs. All right, letter C. Here we've got a function that is just flat across the top. And so it is perfect horizontal line. And we notice that the height, or what's measured on the y-axis, it remains the same. Well, that is indicative of a constant function. The y value, the height, is always 1 in that case. And again, this graph does extend if we were to zoom out. Letter D. Here we've got a function that it looks like it gets really small, really close to 0 off to the left. And then as we move to the right, it grows faster and faster and faster and faster, really steeply growing across the way. And again, here's the tie-in with language. What is something that grows really fast? Well, you may have heard the word in the news or something, exponential. So y equals 2 to the x. Every time I increase x, I am doubling what was there before. That's why it grows so rapidly. And if it's doubling as I increase x, that means it's cutting in half as I decrease x. So that explains why it tails off to the left-hand side. All right, letter E. Here I've got a graph that's bending. And if I plug in a 0, I get a height of 0. If I plug in a 1, I get a height of 1. If I plug in a -1, I get a height of -1. So what over there allows for negative inputs, and it will keep the negative throughout? Well, this is a cubic function. And maybe you went through and tested some x values. I hope you did. That's a neat way to kind of make these graphs make sense. The cubic function also grows really rapidly off to the right. It also will fall very rapidly off to the left. Letter F. Well, here we've got a graph. It's pretty straight, so hopefully just by the shape of a line that's being formed, we would have an answer there. But notice that whenever I move over to an x value, the y value, the height matches that perfectly. So I have 1, 1, negative 1, negative 1, 2, 2, negative 2, negative 2. Again, this would continue. Which one shows that my y value, my height, always matches my x value, my left and right? Linear function. All right, letter G. Here we've got an interesting little graph. It's kind of pointy, but there seems to be a problem around 0. So you'll notice that I don't see the graph. It's kind of racing off vertically when I get really close to that 0 value. So which one of these functions that's left off on the left-hand side is indicating something that breaks when x is 0? Well, the reciprocal function. We cannot divide by 0 in mathematics. So that graph shows what happens when we try to divide by 0. We get something that's incalculable. And then by default, letter H. That must be a quadratic function. Okay, and we can see that y equals x squared. Maybe you were able to associate that x squared with a parabola-shaped graph. But here again, when we go negative with our inputs and we square them, it's like taking a negative times a negative. So it shows that the height should always be positive, regardless of what we're plugging in. Okay, and you have a couple questions here in your note packet that kind of follow up with each one. Justify your choice for each function. We kind of explained those as we went through them on the video. I hope you would be able to explain to anyone why you chose the match that you did. And then number 2, what are general characteristics of these parent functions? Well, let's just take a look back for 1 second. Generally, what do you notice about all the graphs? And the thing I notice is that they're all kind of situated here around the point 0, 0, maybe with a couple exceptions, but most of them pass through or are centered around the origin. And that is a general characteristic that is very important, because as we start manipulating these, transforming them, they will move away from that. So this is like a starting point that we can then transform. Okay, a few different topics, excuse me, that we'll be covering today. We want to set up some nice vocabulary to use all year and in future math classes we may take. The domain of a function. These are all the x values. All the x values that we can input into a function and produce a height there. So where does that graph show up if I'm looking from the x-axis? The range is the same concept. All the y values that are outputs of the function. A function family, these are functions that share similar characteristics. So anytime we see something x squared, we know that is going to have the same characteristics as just regular y equals x squared, the parent. Parent function, again, the most basic function of any family. That's what we just looked at in our introduction. And then we've got different transformations that can move or distort that graph as we move it around the coordinate plane. Translation shifts the graph. A reflection flips it over an axis. And then we can stretch or shrink that graph either vertically or horizontally. So just a quick explanation of domains and ranges and how we're going to write them in this class. We're going to use what's called interval notation. And all this is, it kind of looks like points, like ordered pairs, but instead of it being x comma y, it's referring to a range of numbers. So it's a list of numbers where we are going to get an output, where we're going to have a result. So for letter A, these are the same functions we used for our introduction. We got to remember that if we zoomed out, the graph would continue. So I'm going to kind of sketch in those arrows as we go along. So for this first one, if it continues, as I look along the x-axis, domains and ranges, or x's will tell me the domain, I'm always going to see an output above any x value, right? It's going to continue off to the left and off to the right. So we would say that the domain is all real numbers. And if we're thinking about an interval, those are the numbers from negative infinity to positive infinity. In other words, if we extended this x-axis infinitely in the negative direction, we would eventually get to negative infinity. Well, we'd never get there, but it's over there. And then the positive x-axis tends towards positive infinity. And every single number along the way is going to produce an output in that function. The range, we have the same idea, but now we're looking from where the negatives are to where the positives are. So domains we read left to right, ranges we read bottom to top. And as you can see, when I'm looking down here, there is no graph there. It's not until I get to a y value of 0, a height of 0, that I start to see that graph, and it continues to positive infinity. Now, one thing you'll notice about the interval notation, I used a square bracket there. That means it includes that value. Whereas rounded parentheses means it does not include that value. It goes right up to it, but does not include it. For letter B, here my domain, I see that at 0, and it goes on to positive infinity as I read that from left to right. It's going to continue on towards positive infinity. However, you'll notice that my interval does not include any negative numbers. I cannot plug a negative into a square root. We said that was a square root function. For my range, same thing. I do not see that graph height-wise as I'm scanning from bottom to top until I get to a height of 0, and I will continue to see it all the way up to positive infinity. Even though it doesn't look like that, the graph is going to continue to rise infinitely, albeit very, very slowly. For letter C, domain, scanning left to right, any real number can be plugged into that function. The range, the output, the height, however, is only going to be a height of 1. So since it's only one value, we just see that for a second, an instant, as we're moving our scan from bottom to top. We use one number inside closed brackets, including the 1, but nothing else. All right, letter D. Here, my domain, negative infinity to positive infinity. The graph continues in both directions there. It will continue to move to the right, even though it looks like it gets steeper and steeper. It does, but it is just going to inch its way along. And every x value we can input into that function and get an output. For my range, this is going to be a little bit deceptive. We talked about the exponential being that I started at 1 when I plugged in an x value of 0. And we said that every time we increase x, it doubles. I'm multiplying in another 2. As I move to the left, as I decrease my x value, then it is being cut in half. That height is being cut in half. So it goes from a height of 1 to a height of 1/2 to a height of 1/4 to a height of 1/8. If I keep taking half of something, am I ever going to get to 0? No. I'm going to get really, really close to it, but I'm never going to actually get there. So we do not use a bracket on this 0, but our graph gets really, really close to it. So we use a rounded parenthesis with 0, and then, of course, we'll see those heights the rest of the way up to positive infinity. With infinity, I don't know if I mentioned this or not, but with infinity, we always use a parenthesis there just because we can't actually get to infinity. We can't include infinity. It's kind of abstract. For letter E, again, this graph will continue, and it continues, again, really, really slowly to open up if we were to keep zooming out. Yes, it's really steep, but it does continue to cover our x-axis, so the domain is all real numbers yet again, and the range as well, negative infinity to infinity. Every single height from bottom to top, this one's easier to see, is covered by that graph. Letter F, this one should probably be the easiest one. We've got a line that continues, and it's slanted. It's not perfectly horizontal like we saw up above. So every domain, every x value is hit, and for our range, every y value is hit. Now, for letter G, this one's interesting. If I think about x values, I'm getting heights, getting heights, getting heights, and then at 0, it breaks. And as soon as I get past 0, the graph reappears. So for my domain, if I'm reading this from left to right, I'm going from negative infinity all the way up to 0, not including it. And then I've got another interval that goes from 0 to positive infinity. If I want to include both of those, we put a U in between them representing the word union. And for range, the same thing is going to happen, oddly enough. At negative infinity, we're down at that height, the graph is there. However, when we get to the x-axis, when there's a height of 0, our graph does not exist there. So we have that same thing. We just skip over the height of 0, and then the rest of the way to positive infinity, we will see that graph. And lastly, letter H. Domain. This graph is going to continue to open to the left and to the right. So our domain is, once again, all real numbers. And our range, similar to our absolute value, it does work at 0, and it will continue to work the rest of the way up to positive infinity at the top. So a little bit of time to explain this slide, but domain and range is something that if you understand the patterns of it and what makes a function produce domains and ranges, what messes up a domain and range, can be really, really helpful to take some time and learn these patterns. We're going to be talking about them an awful lot. All right, first example, identify the function family to which the function belongs. Compare the graph to the graph of its parent function. Well, f of x, negative 2x squared. Okay, so that x squared is a dead giveaway. It's a quadratic function. It's in that family. And we notice that it's not your typical y equals x squared. Here's what y equals x squared would look like. What's the change here? Well, we can tell that it's been vertically flipped. The graph we're given opens downward when y equals x squared usually opens upward. You'll notice that it has been moved off of the origin so that the bendiest part of that graph is up at a height of 3. So it's shifted up 3 units. We don't even need the word shifted there. All right. And then secondly, I noticed how where these join, it is 2 units to get to the bendiest point, the vertex, in our blue function. However, it is only 1 unit in our typical y equals x squared. So it was also stretched vertically. I just call that 2 times as tall. And what we're looking for here is we're just a general comparison. What are the changes that we notice? And we want to make some type of connection with what the numbers in that function are doing to contribute to that change. For number 6, here we've got the function f of x equals 3. And, well, this is a constant function, maintains a constant height. And the parent function is y equals 1. So that has only been shifted up 2 units. And we could have just said up 2 units if we wanted. Example 8, you purchase a car from a dealership for $10,000. The trade-in value of the car each year after the purchase is given by f of x equals 10,000 minus 250x squared. What type of function models the trade-in value? Well, hopefully we'd be able to answer this immediately and see that x squared and know that it's quadratic. But let's just take a look. Again, the calculator can help us out quite a bit. So here I'm going to turn on my calculator. And let me just move this so I can see what the function is. All right, f of x means the same thing as y. So in the calculator up here, we've got a y equals button. And that will allow us to type in any function. So I'm going to type in 10,000 minus 250x squared. All right, I'll hit enter. And if I graph that, well, it looks like a couple of vertical lines. What's happening is that graph is so steep that we're not really seeing it very well in our viewing window. So what we can do is we can adjust the zoom, and there's an option all the way at the bottom called zoom fit. So again, that was the zoom key, and then we just use the arrows to toggle to zoom fit. And if we hit enter, you can see it redraws the graph. There we can see a nice parabola showing up there, again, confirming that it is, in fact, a quadratic function. Okay, so our answer is quadratic. All right, and you could see by that graph that negative 250x squared, it is declining in value very, very steeply. Sad but true. All right, graph the function and its parent function, then describe the transformation. I'm going to start by putting both parent functions on here. I think it's nice to be able to draw a basic parabola, a basic absolute value graph very, very quickly. So for number 12, we know that the parent function is involving the origin or really close to the origin, and then go up 1, over 1 from that vertex in either direction, over 2, up 2 squared, over 3, up 3 squared. And that's just using inputs and outputs and a little bit of symmetry to graph that function. That's a good one to have, have in the memory bank so we can graph those pretty quickly. And an absolute value graph, the y value is going to equal the x value. And if I go negative, the y value will equal the positive version of the x value. So we can see kind of these rays with a slope of 1. So there we have our parent functions drawn in. Now for the actual adjustments that we've made, x plus 4 and then squared. So if I make a table of values to graph this one, if I plug in a negative 4, then I'll have negative 4 plus 4, 0, and then squared. So the point negative 4, 0 is on that graph. Oops, that should have been negative 5. If I plug in a negative 5, then I'll have negative 1 squared, which is positive 1. And if I plug in a negative 3, I'll have 1 squared, which is also 1. So you can see we're getting the same type of shape. It's just been moved. So that plus 4 is moving this graph somehow. If I were to plug in a negative 6, I would have positive 4. And if I were to plug in negative 2, I would also have positive 4. So we can see our graph here has simply been shifted 4 units to the left. Which is weird because you would think that plus 4 added onto our x value would move it to the right, but that was clearly not the case. Interesting. Well, number 14. Let's see what would happen here if I made a quick table of values. So if I plug in an x value of 0, okay, here, x value of 0, then my output of this function would be 4 plus the absolute value of 0, so it's a positive 4. If I were to plug in a 1, I would have 4 plus the absolute value of 1. If I plugged in a negative 1, I would have 4 plus the absolute value of negative 1. That's just like 4 plus 1 again. So now our graph, and we could continue our table, but now our graph has been shifted upward. Interesting. So 4 units up for that transformation. So I want you to look at those two and kind of see if we can't come up with a pattern there, and then especially as you're going through your homework assignment, see if we can't confirm some of these patterns that we're discovering right here today. Example 4, graph the function and its parent function. Okay, so let's put those parent functions back up. I should just have those saved. Okay, there's our regular x squared and our regular absolute value. When I say regular, I mean parent. All right, and then let's look at a table of values for each one. So for number 22, if I have an x value of 0, then the output would be 1/3 times 0 squared. Okay, so interesting, they have that point in common. If I were to plug in a 1, then I get 1/3 times 1 squared. 1/3, okay. If I plugged in a negative 1, I would get the same result since squaring would get rid of that negative sign in the process. If I plug in a negative 2, 1/3 times 2 squared is 4/3. 1 and 1/3. And I would get the same thing if I had gone in the positive direction to positive 2. Again, since the negative is getting washed out by that power. Well, I don't really have a very good idea about what's happening. Let's try some more values. If I plug in a 3, 1/3 times 3 squared, 1/3 times 9 is 3. So we got the 0.33. Of course, the same thing would happen if I did -3. So we can see here our parabola forming, and we may want to test some more values until we saw more of that U shape being formed. But it looks like they took that red graph and just kind of smushed it downward, didn't they? It is 1/3 as tall. It has been compressed to 1/3 its height. All right. Now let's see what happens with our absolute value graph. And if I plug in an x value of 0, my height is going to be 1/2 times the absolute value of 0. So again, they have the origin in common. If I plug in, let's move away a little bit. Let's go 4. If I plug in a -4, 1/2 times the absolute value of -4, that's just like 1/2 times 4. It's +2. So at -4, I'm up to 2. And at +4, obviously the absolute value would produce the same thing. I'm up at 2 as well. And you can quickly see that we're seeing that same type of compression. They're kind of crushing it down like a soda can. It is 1/2 as tall. So let's take a look at where those fractions are. Are they grouped in with the x value, or are they outside the grouping, because that's affecting our result? Form some patterns. Example 5, use a calculator to graph the function and its parent function, then describe the transformations. So let's pull up the calculator once again. Remember that this h of x and f of x, those are just the names of functions, and x is our input. Here, if I pull open the calculator and just, can I squeeze that in? Well, let's do the -x plus 5 first. So first thing I'm going to do in this calculator is zoom, and then option 6, you can see it says Z standard. So I'm going to hit that, and it just takes me back to my normal viewing window. All right, now I'll go back to y equals and hit clear to get rid of the function that was there. The first function is -x plus 5. And then the parent function, well, it's just like y equals x, but then they added in some extra stuff to it. It didn't start off as x squared, didn't start off as square root x or absolute value x. So the parent function, which I'm entering as y2, is just y equals x. So I hit enter, and then we graph it. There is the function we were given, and there's the parent function. So what are some things that we are seeing? We are seeing, first of all, our graph is not looking like this parent function that rises to the right. So ours has been vertically flipped, and then it's been lifted up 5 units. So vertical flip up 5 units. Let's take a look at the second one. 3/4 absolute value of x plus 1. All right. So now go back to y equals. I'm going to clear out those. For absolute value, if you hit the math key, toggle over to number, option 1 is ABS. So absolute value of x, and close it up. There's the parent function. We'll do that one first this time. Then the second one, 3/4, so in parentheses, 3 divided by 4 times, then we want the absolute value of x, close up that absolute value, and then plus 1. So let's see what happens here as we graph these two functions together. There's our parent function, and then the second one, we can see a couple of things happening. First of all, our parent function was higher, and then it extended all the way down to the origin point down here. The function we were given, f of x, looks like it was shrunk down, and it actually didn't go all the way down to reach the origin point. It stopped at 0, 1, and then angled back up. So what we would say is it's 3/4 as tall and 1 unit up. Always nice when we can incorporate the technology into this as well. So excellent practices there. We said this one was a vertical flip, and it was up 5 units. This one was 3/4 as tall, and it was up 1 unit. Our last example, here we've got the battery life of a computer over time. What type of function can we use to model the data, interpret the meaning of the x and y intercepts? That interpreting the meaning is huge. When you start looking at, oh, I hear the question all the time, why are we learning this? When am I ever going to use this? The patterns behind it and knowing how to interpret these real life situations. Hopefully, as we go through this, this class, you'll find meaning in the math, and it really is a nice wake-up moment for why we've been learning all this. All right, so let's set up our axes. So I've got my y-axis that measures the battery life remaining, and it's going from, I see 80% and 0% down there. So I'm going to count this up by tens. So we got 10, 20, 30, 40, 50, 60, 70, 80, 90, and then 100. And then my x-axis represents the time in hours that this computer has been on or running. That's just going to be by ones. So we've got 1, 2, 3, 4, 6, 7, 8, 9, 10. Okay, and then of course we've got 0.00 as our origin point. Let's plot the points that we were given. So we've got the point 180, got the point 340, 50, 620, and 860. All right, well, it looks like those points are in a straight line. Let's see if they do follow that pattern, because I might be kind of torn here. Is that looking like a parabola, or is it looking like an absolute value? Well, here I've got 2 points that are pretty close together. Let's see what happens if I continue that rise over run. So 2, 1, 2, 1, 2, 1, 2, 1, 2, 1. Here were the points we were given. So it definitely looks like that makes a straight line. Let's see if it holds to the left, right? It should be going the other way. So up to left 1 continues, continues, continues. So we do have nice straight line data here. So as we connect those points together, they do form an absolute value graph. Value. All right, and interpret the meaning of the x and y intercepts in this situation. Well, our x-intercept, where does that graph meet up with the x-axis? So here is our x-intercept. It's the 0.50. And that indicates that when our x, which is representing time, is 5, the y value, the battery life, is 0. So that's representing the point where we have a dead battery. Dead battery, of course, meaning 0% battery life remaining. Now, the y-intercept. Where does this graph encounter the y-axis? Well, we're going to have to look at our data, and it looks like this point right here. It has to be that point, the point 0, 100. Well, it represents when the battery is at 100% capacity, but it's measuring what's happening when time is 0. So battery percentage when time is 0 hours. So the main thing there, the height is giving us an output there, but the y-intercept every single time will tell me what's the output when x is 0. In this case, what's happening when time is 0 hours, when we first fire up that laptop after taking it out of the box. Really, really nice interpretive question there. All right, that does it for section 1.1. Hope you learned something, and we'll see you next time.